The fourth question for day 16 was to sketch a sensory neuron in an octopus tentacle. We want an odor molecule from a prey item to cause an action potential, and it should detect it using a G protein coupled receptor. Notice I said here you don't need to do anything more than show the G protein coupled receptor, because in an earlier homework problem, you'd already shown how the receptor can cause an action potential. So we need an octopus tentacle. It doesn't say anything about the suckers, so we're not going to add them. And then somewhere we need a prey item that is releasing some chemical. We're going to need a sensory neuron. So here it is. And somewhere on it, it has a G protein coupled receptor, and it's obviously much bigger, which it isn't. It's shown here as much bigger than the dendrite, but clearly isn't. It's on the surface, and so this molecule will bind. That'll cause an action potential, and our sensory neuron needs to go somewhere. And I'm going to do an interneuron, call it A. All right, what do we need it to do? It should cause the tentacle to extend and bend toward the prey item. So how do we get a hydrostatic skeleton like an octopus tentacle to extend? We need circular muscle, which would be better called ring muscle, that's ringing all the way around. This would be out of sight on the back side. And we're going to need a motor neuron to control that. Call it B. And in reality, it probably would be multiple motor neurons, but I am just going to send an axon from this one motor neuron to all the muscles here. So if this contracts, the tentacle is going to get shorter and it's going to extend, because that fluid has to go somewhere. All right, so we want it to extend, so we definitely want an axon from A to B. That'll cause extension, but it won't cause bending. So we also need it to bend in this direction. That would be longitudinal muscle. This time I'll do a couple of motor neurons, call them C and D. One controls this one controls these two muscle cells. And I want to have a branch of an axon go to C and D. Or if I wanted to, I could have a branch of this axon go to another neuron E, which in turn connects both. Either one works. So let's check and see whether this works. Here's chemical is diffusing away. 3, it binds. 4, we get an action potential in our sensory neuron. 5, an action potential in A. 6A and 6B, the two branches from A. And 7A causes contraction in this circular muscle, which is going to cause extension. And 7B causes contraction of longitudinal muscle only on this side, and that's going to make the tentacle bend. So if these are shortening, then the tentacle is going to bend in this direction. So our tentacle will indeed get narrower and longer, and it will bend toward our prey item. So now we want to add neurons to the circuit that would inhibit the movement if there's an odor molecule from a predator. So let's create a predator. And this could be on the tentacle or it could be somewhere else. So here is our predator. And it's releasing something else. Maybe I will make these triangles. And somewhere there's another sensory protein. It has a receptor that can bind that odor from the chemical. We'll send that to an interneuron. I think I'm up to F. And then we want to inhibit this. So I'll draw this inhibitory neuron in red. And there's inhibition. So here we would expect that the neurotransmitter would open chloride channels or potassium channels to prevent action potentials in A. So will it work? We still have this same series of events, but if the predator molecule is there, then we have this, we inhibit here, so we get no action potential there, we get no contraction, our little octopus just stays still.